Hi everyone. Just out of interest, how many people have fine-tuned a model or like have interest in fine-tuning models? Okay, so most people. I can keep things a little more concrete then, because I can, give this talk a little bit higher level when the audience is a little bit higher level. But it seems like people are in it here. But as a motivating question, what is this article of clothing? This is the fashion MNIST data set. If you've spent time in traditional ML, this is a pretty hello world data set where you're just trying to guess, is this a sneaker, is this a shoe? And if you ask something like GPT-4o mini, it gets 81% correct, which is pretty incredible because it was not really trained on the task, but it's also really incredible in the sense that an XGBoost model where you just take that image and you just plug it into a Stats 101 architecture model and you get 90%. And if you train a reasonably small ResNet, you get about 95% accuracy. And really the motivating point here is that models have always been adapted to data. There's this concept, the concept of pre-training a model for arbitrary tasks is very good, but in practice, the world of machine learning, the world of data science was always about mobilizing your first-party data so that you get better results. And it is important here because the data that goes into the language models are not necessarily the data that you have at your organization. So for instance, for RAG, RAG use cases, were hotter and more popular, and we've discovered they're not everything, but it was trained. The first models that are in this transformers category were BERT models that Google trained to be able to retrieve websites correctly. And so as a result, when you use embedding models, you get 95% accuracy retrieving web docs. But for this one law statute benchmark on Hugging Face that I found, is about 49% accurate for retrieving this kind of legal document. And Voyage AI sold for $220 million to MongoDB to solve this problem of adapting embedding models to domains, right? So there's value here, and it's pretty clear that there's a huge gap in the accuracy when you use the model for what it was trained on versus when you use it kind of off spec. The other thing that you get beyond accuracy is that you can get better latency, right? You can take the same size model and make it more adapted to your task, or you can take a much smaller model and adapt it to a task and perform better. So it's really hard to read the small text, but basically what it says on the left is the probability of making a fix, and on the right-hand side, it is the speed. And this is Databricks trained a tiny model that has slightly better accuracy than GPT-4o, which is the teal bar, but it has almost twice the speed. And so you get these cost and latency benefits from mobilizing your first-party data to do it, because it's probably true that Opus 4.1 or Gemini 3 can do your task, but these are trillion parameter models and mixtures of experts, so they're not all active, whatever. But they're huge models, and you can just take a tiny model, and for this quick fix use case, all you want is a tiny model to make tiny edits to your SQL query, and sending that off to Opus 4.1 and paying the token cost and the round trip cost of latency is just not worth it. So this slide just briefly summarizes what I was saying. Domain-specific knowledge, task-specific success, cheaper and faster, which are all good things to have. And I think part of the problem is that you have this very marketing-centric ecosystem happening right now where it's don't train models. It's so hard. You need to hire someone who's paid $100 million like those Meta offers in order to train models. And this is a little bit of a cynical, self-aggrandizing, oh, we're building such great things, but it also scares people off from doing things. I think the analogy that I would give is either imagine walking to the chief risk officer of a bank and being stop training risk models. Just give us your risk team, fire the entire risk team, and we will be the only people from outside your organization that trains a model that predict risk correctly. The other thing is imagine if Facebook just advertised through Google ads, right? Meta is a $1 trillion company printing money on its ads, but at the outset, they could have just used put some Google ads on the corner like you get on small websites. But instead, they collected that data and mobilized the data to create a really good ads network. So ML has always been about winning with data, and so The last motivating thought is that every model has been fine-tuned. And I think this is now obvious to people, but you have a pre-training step, right, where you kind of take the entirety of the internet and everything you can scrape, and you do this massive pre-training, self-supervised almost, to kind of just like learn the generic patterns of images, text, whatever, right? You have these models like Dino v3 that were released by Meta that were just self-supervised learning over images. So you have these pre-training step, and then you have some post-training. And increasingly, you see that the post-training is adapting the models to increasingly complex tasks. So if you think about like why Cursor or Lovable is so good, you go back about a year, GPT-4 comes out, and on things like SWE-bench, which is a coding task benchmark, you get something like 30-something% accuracy on the state of the art a year ago. DeepSeek comes out, and it did significant post-training over like verifiable like coding tasks, and it moves that benchmark accuracy from like 35% to 60%. And then you take that same technique of extending the inference time compute, and you doing some post-training with reinforcement learning, and you kind of see these like frontier labs like OpenAI and Claude kind of climb their way up into like the 70s, and I don't know what the current like frontier, but it's like mid 70s, right? So through post-training, by adapting it to a coding task, you got basically more than double the accuracy before you did this specific post-training task. And it allows for applications that build on that model, like Cursor and Lovable, to suddenly do magic, whereas if with 30% accuracy, they simply could not. So for me, a lot of the tailwinds of like why did Cursor grow so quickly was actually because of a post-training exercise that was a research exercise unlocked by DeepSeek that then like percolated through the ecosystem. And so you have all the data, right? Like coding is a generic task that exists out there in the world. If so many of the talks at this conference, and in general, it's correct, that you need to collect evals, and there's all these tools to help you collect evals. This feedback data is just incredibly valuable training data that you should be using to mobilize for model fine-tuning. You can do things like super SFT, soft prompt tuning. I believe there's going to be a talk on that later, which is not the same thing as just like prompt engineering, right? Like you're actually doing a little bit of training on the prompt. LoRa for like kind of parameter efficient tuning, right? Like you're multiplying a bunch of matrices together. What if you could just add one more matrix that you multiply at the end? RL, as I mentioned, right? It's about generating an evaluation environment that kind of grades outputs. You have an inference service that produces outputs, and then you have a trainer. So then your inference service produces some results that passes it into your evaluation service, which gives it rewards, and then feeds that back into your training service, tunes the model, which then updates the inference service in the loop. And then, I think the last thing is like, this is maybe a hot take. Prompt engineering doesn't scale, right? Like you get to a certain level of accuracy, and then your prompt is huge, and then you like change something about your prompt, and then suddenly like everything falls apart. A new model comes out, and everything falls apart. It's just not a like very deterministic or like reasonable way to do engineering, right? And I think it's like fine for like prototyping, but you do reach a threshold at which like you would want an objective way to like march up the gradient. Like there's no like gradient that is like that you can move along for prompt engineering. It's really like spray and pray, right? And eventually it like gets good enough, and your system might be sufficiently satisfied by like a pre-trained model in your prompt engineering. But like when you're doing training, for instance, on like reinforcement learning, or you're taking the user thumbs up, thumbs down from interacting with your chatbot, that like directly marches you up the gradient of improving your system. And like there's this fear that like models will erase my hard work. And this has maybe been true, right? Like if you spend all this time as Cursor building like a system on GPT-4o, and then accuracy triples, then you're golden, right? Like you didn't need to do all of that work. So yeah, like I think you want to build a data system, and this is generically true for all machine learning and data science, right? You start with the off-the-shelf models, and then you build some robust evaluations on that. I'm not saying that you shouldn't build robust evaluations. And then you take that evaluation gauntlet, and you can turn that into an offline data set where every couple weeks or every month or every couple months, you take that offline training, you take that offline data and you do one big research loop and try and improve your model. And then eventually, like you build your user base, your YC company, you scale a bunch, and you have all those users. You can take your online data and then just like propagate that on the fly back into your system automatically. And that starts to feel a lot more like, if you think about the traditional world of ML, when you're like scrolling Instagram and you're scrolling those Reels or TikTok, TikTok is retraining the recommender system every 15 minutes based on your online activity. And like whatever, you can debate me on whether that's offline or online training, but like the way that TikTok is really good is that literally your user activity propagates back into their recommender. And like under the hood, like now like descending level, like tuning is just like PyTorch training, right? So like there's a lot of expertise already out there. There's a lot of code samples. You can just use prepackaged things like the Hugging Face trainer, or you can use vanilla PyTorch, or you can use any number of frameworks. And it mostly looks the same as like training any other model that has existed in the ecosystem. But they feel different because the weights are suddenly higher. I think you have a lot of teams who spent their time training models, maybe single GPU on a notebook, and that feels okay. When the model weights grow by order of magnitude or 2 orders of magnitude, then suddenly you have a problem where your like infrastructure starts to become a little bit more tricky, and I'll get to that in a minute. And then there's also this problem where like a lot of teams don't have a target metric. Like if your goal is like, oh, my VP told me I needed to deploy a chatbot this quarter. What is this chatbot going to do? I don't know, right? And then you don't really have like a good like way to like improve your system, and so go do that first. But then, like, once you solve the infra problem and the data problem and the target metric problem, you can do a LoRa training for $100, which for most people, even as individuals, is like not crazy. The point about the ML platform is, I think, more salient to me, and it's like what we work on, right? At Runhouse, we build an open source library to bring ML workloads to Kubernetes, so spend a lot of time with ML platform teams and spend a lot of time in the infra layer. But like, most teams don't have a proper ML platform that allows them to launch and experiment with multi-GPU, multi-node like setups. If you're notebook-centric, you're somewhat limited in scale. If you're working on a dev box, you're somewhat limited in scale. And you also don't have really good reproducibility when you use notebooks because JSON files are not code, maybe also opinionated. An okay temporary solution is that you can shove your workload into whatever fits into a single node. And like I view it as both like a positive pattern and a little bit of an anti-pattern that things like Ollama or like Axolotl have so much popularity. Because that is about like the fact that your platform cannot support arbitrary methods, and therefore you must take very specific methods and like kind of like shoehorn it into like a library framework that like allows you to work in a limited domain, rather than like maybe over the longer term wanting to like take your platform and evolve it into something that allows you to kind of train more generically. And even for the teams that have some kind of ML platform, the state of the art is like development through deployment. And this is maybe a little bit subtle for people who don't really spend time with like Kubernetes or redeploying training jobs. But if you think about traditional software development, you can test locally. Like if I'm building a website, I can look, I have an image, I change the alignment, I can see what that looks like locally before I deploy it to my Kubernetes, and I scale it up to 1,000 replicas and I serve the entire world. In ML, you don't have a GPU attached to your local machine. So if you're not SSH'd into the head of a VM, if you're not SSH'd into like a VM and you're not like working directly on like a local environment with a GPU, you have to deploy your application in order to see what a print statement looks like. So you add a print statement to your training, then you tear down your existing training, then you repackage the Docker image, push it to your container registry, bring up new pods, load in the data, load in the model checkpoints, bring the checkpoints into GPU memory, and then the 15 minutes have passed, just for you to hit like a print statement to see, and then re-loop through that 15 minutes. And so that creates really bad development velocity and drives people back into using like notebooks, which has really good development velocity, but doesn't necessarily allow for like reproducibility and like recurring training. And then like I think this like all percolates down to a concept, and you know people love like giving terms to things. It's like there's experiment escape velocity. I think a lot of teams don't do training because they look at the complexity of the task ahead and about like how much work it's going to be, and say this doesn't have the velocity to escape like our planning session, right? And so it gets stuck as something that like people want to do and like conceptually want to do, but even when you see an open source repo, you're like, well, but like we just can't run this repo on our own data, and so then it gets stuck in planning, and like training is always like 4 months away for a lot of teams. But like the model that I think like is really interesting to think about on the infra side of the world is Snowflake. So before Snowflake, you had SQL queries that were all running single box. You would like SSH into a server, like the SQL server or Oracle server if you're unfortunate, and then you would like run your queries and it would work. And then if you had more data because you ran out of disk or your queries were running too slowly, you would eval your DevOps team and they would schedule some time and they would move you onto a bigger box. But then Hadoop came and you had distributed infrastructure for like running queries, but Hadoop was hard. You had like separate people doing Hadoop queries, managing separate infrastructure. And so why Snowflake was really good, for me at least, was that you could just take anybody 2 weeks out of school with an arbitrary SQL query, and it could be 10 rows of data or it can be 10 billion rows of data, and you just execute it from any environment, like from your browser, from your local machine, from your Airflow DAG, and it would just dispatch that query out to Snowflake, which then magically distributed it for you, and then executed and then returned the result. And you no longer needed to think about compute, where your query was running, how to structure query. All you had to do was kind of have code and dispatch it into an execution environment. The execution environment is increasingly for us observing the ecosystem. Like we rebuilt our entire product around Kubernetes. Like it is increasingly Kubernetes. Kubernetes is proven at scale. It is has a really rich open source ecosystem. It is really the only way to like efficiently do compute. And so like we are building KubeTorch. There are other ways to approach this. Like obviously I have to bring it back to the product that we build. But really what you want is a Snowflake-like experience for your distributed training, right? The fact that you have a really large language model that needs 16 GPUs should be somewhat abstract to you, and you should be able to just write the Python code for the training and have that execute. Because in Snowflake, if you're running over 10 billion rows of data, you no longer have to do the Hadoopy stuff, which is like rewriting your query and conforming it to like a DSL that runs in a very narrow way. So before KubeTorch and like our easy interface into Kubernetes for scale, there's that problem where you have to redeploy for every single test change of code. You have steep learning curves where like you have YAML, which is not really code either. You need to learn about like Docker and cloud services and all of these things. And then if you built things in a notebook, you would like take that notebook, you would hand it off to someone, and they would take 1 week to 3 months to turn it into a production pipeline. And that was a bad experience on both sides. Other teams, like, sometimes people kind of give you a gunpoint and put you at gunpoint and then say, like, you have to translate it yourself. And then other teams, like, have different versions of that. But, like, the whole MLOps thing just really reflects the fact that, like, you couldn't just work out of a mono repo and just, like, run code arbitrarily the way that, like, a data engineer would. With KubeTorch, all these problems are solved, obviously. Green check, green check, green check. And it's a little bit unopinionated. So really, like, just to give you a little bit of like the APIs that we're building for like making training and batch data processing, et cetera, very easy, you kind of just define your compute in Python. It's Pythonic, it's not YAML. And then if you want to say, I'm going to do distributed training, you just say .distribute PyTorch. And if you think about what happens in Kubernetes is that if you have one replica, it's one GPU in the pod, and then you say, like, I want 4 replicas, and we just wire up the distributed communication on like 4 pods for you, and then everything just works. You take your trainer class, which is locally defined in your model repo or whatever, and you just say, I want to send it to the GPUs. The term KubeTorch is really like indicative of what's happening, right? Like if you're using Torch for GPU training, what's happening? You're doing model.toCUDA, you're actually producing a copy of your model in GPU memory, and then when you call model.forward in like your CPU process, it's making that call out to your GPU, doing the computation on your GPU, and then returning the result to you. But all of that is abstracted from the user, right? And as far as the user concerns, they have some training code, they have their model, and they just have moved it to the GPU. In the same way, you have some local training code, a regular class or function, and we move it to cloud compute for you in the same kind of abstract zero-cost way. Inference is also important, not just because you care about inference, but inference is becoming increasingly important for reinforcement learning training loops. And so, here's like just a little bit of a different decorator pattern for how to do inference. And then when you can, what you can do then is just call like by name the inference service. And this works really well to deploy to Kubernetes as well. If you're using a third-party inference service, I don't really know how you would do some of the reinforcement learning loops where you would have to do some inference, update the model based on evaluations, and then do the training and then update the inference service, right? Like that loop of RL requires you to be able to deploy both inference and training. And so like zooming back out again on like a few things for you to like think about and try. You can run continued pre-training by feeding a large number of tokens in your domain into like an embedding model or a language model and try and give it some more domain expertise. You can distill large model behavior into a smaller one. So go out and just do a bunch of inference over your like sample queries on like the biggest model you can find, and then take that and just take those tokens and feed that into a really tiny model and hope it learns the behavior of the large model. And you can kind of see this in like the distilled versions of DeepSeek, Qwen, et cetera, where they train the really large model and then they very quickly get the smaller model to perform roughly as well on specific tasks. You should create a high quality label data set. You should like sit down with a team and have everyone label 100 examples. And this will be your like ground truth, highly well validated ground truth data set for model performance, but also for fine tuning in the future. And every time a new model comes out, you can just take this high quality data set and just run it. And then finally, you should take your user feedback. I already talked about this, but you should take your user feedback and propagate it back. Character AI, when they were just released, if you were like generating like, I don't know, your AI friend or AI girlfriend, you could swipe and they would regenerate the character for you. And that was just propagating directly into their like training loops, where if you say, I don't like the looks of this image that was generated, that's like the biggest signal that like you have done something wrong as a model, and that propagates directly into a gradient of improvement for your model. Whatever, this is a slide. If you're interested, but you're like, oh, I don't have any compute, we do have a serverless option. It's also open source, so you can install it in your Kubernetes cluster. I think I'm running low on time or okay on time? Okay on time. So then I'll talk about this a little bit more. Like KubeTorch just deploys that by a Helm installation and a Python client. If you're using Kubernetes, that should be relatively familiar to you. If you just want to play around with like distributed training, but on somebody else's cloud, we do have a serverless option. Then you can, it's early for us. We're a small company. Find me and we'll get you set up. Think about it as just like somebody else's Kubernetes management, but just entirely regular, and you can use it as is on your own cluster down the line. There's no difference in the software installing on either. It's just the management of the cluster. And so I can take a couple questions after this, but key takeaways, always start with valuation. There is no magic. I am not misaligned in any way when I say you should do training with all the people being like, oh, like evaluations are super important. There's a lot of vendors for that. You should go out and pick one. Maybe some of the friends that are sponsoring here. But once you have that valuation, you must do something with it, right? Like we used to like measure model drift in like traditional data science and ML. And it's like, it would be insane if you were like, oh yeah, the data has drifted, but like I know that the data has drifted. I'm not gonna retrain my model. I'm just gonna like watch it be misaligned with like the input data. So you have the evaluation that tells you what you wanna optimize, and then you can start mobilizing your data to introduce like the magic into your AI systems, right? Like I said, the magic of like training the model to do coding unlocked like billions of dollars for like Cursor and Lovable, and you are doing something probably very unique and specific, not a generic task. I wouldn't say you should go out and go fine tune for like coding tasks generically, but like what your company does narrowly is not going to be tuned for. Maybe like a side point, like I don't know if this is the Bay Area, maybe people know like companies like Mercor or like these companies that are being paid like hundreds of $millions. Like I have a friend who used to be in PE, and now he's being paid $150 an hour by OpenAI through Mercor to like make financial models. And so the point of that is that like OpenAI doesn't have financial models that it can train the models to be really good at building. So therefore goes out and spends $100 million paying people like my friend to like build financial models for them. But if you work at a bank, you have all the financial models in the world. Like you're saving $100 million on like that first party data. And like it's actually really silly to me that like JP Morgan is not, you know, training its own models to like replace investment bankers, rather waiting for OpenAI to train you know, third party models to replace investment bankers. And then finally, like your platform should make you not scared to like try things. If you waste a whole quarter and like don't produce a result at the end of it, that was a bad use of planning. And so like there's a little bit of this like, hey, like now is the time to finally square the problems with like ML infrastructure and good platform engineering practices. Because like if you have a good platform and you can just run arbitrary code at any scale, then you're golden to be able to do these experiments. If everything is a slog and it takes a really long time to run anything, then yeah, it's probably not worth it to do a lot of this model training. Yeah, and that's it for me. And if anyone has questions, we have 5 minutes, I guess. Yeah.
So hey, Runhouse itself is basically sort of just a fake Kubernetes system that solves all that problem.
Yeah, you can think of it like, depending on what you're most familiar with, like KubeTorch is like the open source library that just, you can think of it as an interface into Kubernetes for developers. You go out to Google Cloud and you buy a GKE cluster and you buy some reservation of GPUs, and then you go like, okay, how do I use this Kubernetes cluster now? It's just like a Pythonic interface into Kubernetes where you like take your code as defined by regular functions and classes, and you call that API like .to. And what that will do is deployment to Kubernetes, and then future deployments as you iterate your code take like 1 to 2 seconds to iterate, even when you're working at distributed scale.
So then the second question on top of that, how much
do I need to do on the data side? So great, I buy your product. What do I actually need to do in terms of collecting that high quality data, and how easy is it to do that, or are there tools for that? But that would strike me as the other problem is great, yeah, but do I really just collect all JP Morgan's models and shove it in there, or is there, what else needs to happen?
Yeah, that's a really good question. Depending on what you do, some training is just shoving it all in, and I think increasingly you see like these like RL loops. Basically, like the RL loops like are kind of proven to work if you have some ability to measure the success. So like for code, right? Like the reason why RL works is like you have a model and you generate like, so you have some like sample questions, right? Like you have 1,000 coding input prompts. So then you have the language model generate the answer for the 1,000 input prompts, and then you have an evaluation sandbox where you take the code it generates and you try and run it. If it hits a bug, you say that's a negative reward. If it hits success and produces the output you expect, that's a positive reward. And so then you collect all of these rewards and the outputs of the model, and then you take those rewards and the outputs of the model and you put it into your training service, and then the training service basically says all the things that succeeded we want to like upweight, and all the things that failed we want to downweight. And so you kind of have just like these 3 components, which then you can then think about in like neat way, like neatly separate. The training service is entirely regular, like PyTorch distributed training. You have some ML engineer who can like do that if you hand them the data. You have an evaluation service, which is just to say, like for this particular thing, do I have a ground truth to compare the outputs of the model? And so for the JP Morgan financial model case, it's like, hey, build a financial model based on this input data. The AI model will build the financial model, and then you have a ground truth financial model, and you like compare the cells with each other, and it's like, oh, it either did the math correctly or it didn't, or like it did the cell like calculations or not. And then that comparison, right, based on the number of cells that look the correct and like other things, then you propagate that into like the rewards. So like I think the RL is like increasingly the popular one, but like what I was saying for like for instance, the domain expertise embedding model, right? Like something that you could just start with is just like shoving up like millions. If you're in like pharma or something, you can just take like an NIH database of all the PDFs of all the drug applications that have ever been filed, and you just like shove it through the embedding model, and then the embedding model will just get better at like determining the resolution of like things in that domain. And like I can't guarantee it without having run the particular experiment, but it's like generically true that like the original like embedding models were trained to like retrieve websites, and they just shoved all the websites through it, and then it got really good at retrieving websites, and you can shove other information into it and get better at retrieving that information. So there is heterogeneity in like what you should actually do, but like there exists probably some, like if you Google like how to do your thing, like there probably is someone who's doing it in open source.
A couple of questions.
Couple questions.
Yeah.
I see what you just provide the Helm chart and Python
Yeah.
and PyPy libraries, so anybody can install everything. Is it open source or
Open source, yeah.
do you have GitHub?
Sorry?
It's an open source library.
It's open source. It's on GitHub.
Okay.
You can.
And can you give me why, for example, it's better than Hugging Face Accelerate?
So
Can you compare them?
Hugging Face would be like, I think at the program level, right? Hugging Face, like if you're using Hugging Face Accelerate with Hugging Face Trainer, that's really good because it like helps abstract the training for you. But then like you want to run the Hugging Face APIs over 16 GPUs. How do you take your code, which is the Hugging Face Python code, how do you run that over 16 GPUs? Like the standard would have been actually like, I think, Dockerizing your application, pushing it up, and like having like either 16 or 2 pods, depending on how your like GPUs are structured, and then making calls against the entry point on both of those pods, right? Or you can use something like Kubeflow PyTorch jobs, which makes identical calls. The whole principle function, like the whole way that PyTorch distributed training runs is that for every replica, you make an identical call to it with like something like torch run, and then it will run all the replicas. But the actual underlying application and the abstraction, whether you're using Lightning or Hugging Face Trainer or whatever, that's entirely your choice. The problem is like, how do you get that to run on 16 GPUs is like what we're trying to solve. Like the interface into compute is what we're trying to solve. But we don't actually care about the underlying method, right? Like you can use Hugging Face Accelerate with Hugging Face Trainer, which is all the abstractions over PyTorch. That we don't really care about. That would all live within your like my fine tuner class in this code example, right? So you would implement like a train method on this class, and that train method would essentially use Hugging Face to do the training, right? So that's at the code level, and then we do the packaging and deployment.
Okay, thank you.
All right, that's your time.
I can hang out in the hallway,
Yeah.
and if you have another
And
question.
I believe food has begun to arrive, so. Oh, no, we have it until 30, that's what it is.